Can't work. Oh, yes, yeah, this, the laser.
Okay, hello everyone. It's my pleasure to be here to introduce our work, and especially after our distinguished Professor Einstein. And my name is Zhenhua, and from China University of Beijing, and I'm now in the associate professor. And my boss is Zhenhua. I will introduce our group works on integrated technology of CO2 geological utilization and storage. I will introduce from three parts, and the first one is the research background. We all know the global carbon emissions continue to grow, but global energy demand remains strong. So it gives birth to CCUS. What's the CCUS? CCUS is carbon dioxide capture from company or direct capture from the air, and then to maybe to inject to the underground to enhance the underground energy, the recovery, and also can be used to form the materials like the cement. And at the same time, the carbon dioxide can be storage, so it's called CCUS. Our research is most focused on the underground, so it's more details is CGUS, geological utilization. From this processes of CGUS, we can find some key issues. So the first CO2 will be injected into a reservoir. So the first issue is about the CO2 corrosion of wellbore. And CO2 injected to the underground and enhance the underground energy. So how about the balance between the recovery and storage? That's the second issue is the synergistic of recovery and the storage. And we also worry about CO2 injected in the underground, that is safety, and how about the CO2 migration and transportation. So around these four key issues, we get this research progress. And the first one is about the CO2 corrosion of pipeline and wellhead. We constructed a corrosion characterization model for pipeline and the wellbore CO2 injection at actual scale, and also consider the washout height to quantitatively characterize the degree of corrosion affected by key factors. And the second work is a multi-field coupled simulator. We focus on the underground oil reservoir. So if we want to describe the CCUS UR system, and we need to consider this specificity like CO2 is miscible with crude oil and will change fluid property. And also CO2 is an acidic fluid, and he will break the chemical reaction balance. So from the modeling scope, we need to describe this system. We need the species like CO2, water, and hydrocarbon, and heat to describe the non-ethanol. And the phases need include the gas, liquid, and oil, and solid to describe the rock. And we need to also to consider the mechanism like the distribution, extraction of CO2 and oil, and reacting transport include the convection and the dispersion of components, and the ionic complexation, and the minerals dissolution, and the precipitation. And under our investigation, we found about the EOR simulators. They have limited chemical reaction consideration. But for the geological separation software, but they doesn't account for multi-component oil phase. So the problem is there's no wonderful software to describe the chemical reaction processes under the oil reservoir. So to solve this problem, the first work is to do the software development, and this work is based on the TAPRACT. This software is published by the Lawrence Berkeley Lab, and also wrote by my PhD director, Tianfu Xu. And my work is under this TAPRACT to introduce the oil phase into this program. We can see the TAPRACT, the species include the water, CO2, and the last one is represented the rock. If we want to introduce the oil phase, we will add the many kinds of hydrocarbon, and the rock is become a boundary of our model. And also induce the oil phase. If we induce one phase, but the combination of phase will become more complex. And my work is add the a flash calculation to describe the CO2, to describe the interaction with CO2 and oil, to calculate the phase distribution coefficients between gas, water, and oil to find the CO2 balance between these fluids. And this work is due to the TAPRACT open source framework and the module design approach and use version, and it has a cross-platform compatibility. And after finish the software development, after verified this software through compare with CMG and compare with experiment result, we have applied this software to many complex geological models like non-isothermal. That means our software can be used to geothermal reservoir and the mineral heterogeneous, not only the permeability heterogeneous and soil structure. So to solve the calculate time, we further developed intelligent machine learning integrate repeatedly predict simulator. And now the calculate time is about 0.1% of the traditional one. And another work is about offshore CCUS. We construct a carbon-safe model of seawater to consider the algae photosynthesis to affect the CO2 bubble liquid or methane bubble liquid from the seabed to seawater to see how it will influence the carbon of seawater. And the third work is about the synergetic of recovery and storage. From chemical school, we have construct a new chemical composite system to optimize dynamic synergy of CO2 and storage. And also using CO2 nanobubble to improve the efficiency of recovery and storage. And our group have designed the machine to make our own nanobubble in high pressure. For the simulation, we applied our software and to better form a method for quantifying synergy to optimize the production process. And also I mentioned that our software can be used to the geothermal reservoir, and our group first proposed the integrated CCUS sequestration geothermal potential. That means the CO2 injected into geothermal reservoir, and then the high energy CO2 injected to the oil reservoir to get more recovery of CCUS. And the fifth work is peridotite CCS origin hydrogen technology. And we all know that peridotite are higher in mechanism and cesium than salt. And our simulation has reproduced the mineral evolution of peridotite in increasing CO2 abundance using simple task data, and this sample is from the Tibet plateau of China. And our results show that the precipitation minerals will first the sixth night, and then the final will become the pearls and the magnesium. And so this how this process is relevant to the hydrogen, because we all know the most of natural hydrogen is generated from the synthesization. So we can to define the most suitable conditions to get the max volume of the light, and we have the heat water to get the max potential of hydrogen. The sixth work is in issue phase equivalent and multi-phase transfer characterization and simulation method. Start this page. This work is worked by my college. So our Chinese reservoir belong to land phase sedimentary, and it has strong heterogeneous and fracture development and several CO2 gas churning. So our group developed self-reinforcing, low damage, and supercritical CO2 resident deep flooding system, and has a good response to carbon dioxide. It's stable and expandable. And the last work is about leakage risk monitoring. We developed the dynamic fracture inversion techniques based on flowback production data, and then feathered physics data driving quickly and apparently elevation method. So for the future work, the first future work is we will add the mechanism into our THC software to form the THMC. And this work is to achieve the goal is we want to accurate to describe the CO2 migration and also the minerals grade migration. And the second future work is about hydrogen. We're both interested in natural hydrogen and artificial hydrogen. And natural hydrogen, we want to get the global potential of the natural hydrogen, and we all know the geological structure is also suitable for CO2 storage. And artificial hydrogen is, I just mentioned, the peridotite with CO2 forms the austenite, and alteration of austenite with high temperature water will form the hydrogen. The third future work is about the phase transition characterization of CO2 in the offshore in-situ storage environment. We want to achieve the significant improvements in seabed effective storage rate and the establishment of efficient CO2 storage technology. And the fourth future work is intelligent design and optimize of chemical molecule structure by recurrent natural networks. We want to achieve the automatic evaluation and the screening and the intelligent design of molecule structure. And these are our group's research project on CCUS include 4 items of National Key Program project and also municipal chair, and also the Ministry of Additional Innovation and introduction base, and so on. And this is our race lab, and include the carbon dioxide microscopic visualization and the nuclear magnetite tomography and nano CT and the Roma microscopy. And our research platform includes 2 national key laboratories and 2 international research platforms and 8 provincial research platforms. And this is our groups, and our leader is Zhenhua Ray, and includes 5 members. Welcome to be you the feedback to this email, also raise and mine is okay. Thank you to everyone.
These are a very wide diversity of questions. Any questions for us?
Yeah, that was impressive. It went kind of fast though, and I missed, what is orange hydrogen? I didn't quite get that.
Yeah. Orange hydrogen actually is an artificial hydrogen. Like if some place only have the offline, but not have the high water, so it will generate hydrogen. But if we artificial to add the water, so it will possible to generate the hydrogen. So this hydrogen means orange hydrogen, and natural hydrogen means gold hydrogen. Yeah.
Excellent, comprehensive work, very impressive. You probably mentioned the company, how the THC company with the mechanical company is that. So could you comment a little bit on that? How do you couple the THC model with the mechanical model? How do you couple those two groups together? That's my first question. My second question is, you mentioned about the machine learning model. So I kind of wonder how you train the model. Where are you training data from?
For the first question, for the composite methods, we use the sequential methods. That means like for the THC to for the fluids and chemical is two different models. And for the chemical model, it only influences the water and the carbon dioxide mass for the fluids. So it's for each step to change the mass of carbon dioxide and water to consider to achieve the cover of the THC. And for the second question in the machine learning, we use the data simulated by our own self-will. So we can get this machine, the machine learning, the machine learning program is appropriate for our software. Yeah. Thank you.
We've done pretty small last